All right, and it's time to wrap things up here. So some final remarks with an example. Here, just a definition here. When we talk about a matrix being positive definite, negative definite, whatever, right? Then its corresponding quadratic form is positive definite. That's just a fact. So that's why previously we were looking at, when we were doing Sylvester's theorem, we were looking at a matrix, but then talking about that matrix being positive definite. Well, if that's the case, then its corresponding quadratic form is positive definite. Okay, then we did manage to leave our Taylor polynomials way back at the beginning, so it's time to pick those up and finish that off. So when we're talking about the Taylor polynomial of degree 2, we were kind of confused about what would go here. We know that there's a factor of 1/2 out here, but then beyond that, what we're actually going to see is that we have x, or vector x minus vector a, and then the Hessian of f at a, and then I needed the transpose. Okay, and then vector x minus vector a squared. Okay, which I already have. And actually, I'm going to omit one of those squares because I've already put it out in front. Okay, so I'm just going to modify what I had there. Okay, and this is actually going to be really nice for us because we have the Hessian in there, right? That is a symmetric matrix, so we can apply all of our theory that we talked about with quadratic forms. Okay, so in this example, I believe this is like number 10 from 4.1 in your textbook. But if we want to find the Taylor polynomial of degree 2, and that's what this is meaning, so this is Taylor poly of degree 2, okay, for that particular function. So what I'm just going to do is I'm going to start getting all the different pieces together, and then I'll assemble it all at the end. So I know I'm going to need f at the 0 vector. Okay, that's my point. And when I do this, I just get out 1. I'll let you verify that on your own. And if I look at the gradient of f, right, this is going to be 2e to the 2x plus y, comma, e to the 2x plus y. And then if I look at the gradient of f at the 0 vector, what I end up getting is 2, 1. Okay, and then let's go ahead and make the Hessian. So then this is going to be 4e to the 2x plus y, and then 2e to the 2x plus y on the off diagonals, and then in the other diagonal, should be e to the 2x plus y. Okay, and then when I make the Hessian of f at the 0 vector, what I end up getting is just 4, 2, 2, 1. Okay, and so now I have all the pieces that I'm going to need, right? And so I'm going to say that this is, or that that P2 of x, or T2, okay, it doesn't much matter, okay, is going to be 1 plus, okay, then I have to do the gradient at the point, so 2, 1, and then dotted with x minus 0, y minus 0, alright, and then plus 1/2, and then I'm going to have xy, and then 4, 2, 2, 1, and then xy. Okay, and what this is going to end up being, and this is all the further simplified, I want your answers, please. 1 plus 2x plus y. Okay, so that part is really that first derivative component. Okay, if you want to insert brackets, you can. And then plus 1/2, and then 4x squared plus 4xy plus y squared. Okay, and that's all the further simplified I would really like it. If you have to distribute the 1/2, fine. I roll, but fine. And then I think I just have a few more comments about your homework. Okay, so generally what I recommend with these problems is find everything first, as I did, and then get the Taylor polynomial of degree 2, and then do not multiply out too much. That's A, it's annoying for you, B, it's annoying for me, C, let's not do it because of A and B. Okay, and that's really all I have for comments on your homework and wrapping all this up.